Okay, so the first technique we're going to do, it's kind of an odd one because it doesn't seem like it's based on a lot of science, but I've talked to a lot of people who have actually seen this. Do we have any military people here, particularly Coast Guard, Marines, or Navy? No, there's been out on a boat. Okay, so there's a big storm, you know, somebody's out on the boat, we lose them, right? The radar loses them. We want to search and rescue. Where do we look? The ocean's pretty big, and especially at times. So they're out in the middle of the ocean, they're right here. Well, one thing we can do is just create a big circle and just look in that circle, but that can be a really big circle, and we could miss a lot, because shouldn't it kind of matter where they were going originally? So what if they were traveling, let's say, you know, this was their path, and we lost them here? What would a better suggestion be? In other words, looking here? Probably in that general direction. Now, if I thought of the tangent line right here, so whether you're walking around on a two-dimensional surface, or if you're in my Calc 3 class, you guys know when we talk about vectors and you hit the banana peel in space. I always call it the banana peel in space. Which way do you slide? You always slide in a direction that is tangent to the curve. Now, we're doing a two-dimensional problem, but this is still true in 3D. So as I'm out in the water and I hit the slick spot in the water, hydroplane, I guess technically all boats are hydroplaning, right? So that's a good starting point, isn't it? In other words, that's a bad idea. Maybe that's a bad idea. But I was already turning, so can I use the fact that I was already turning to help me have a better search area? So what if I said, you know, based on my predictions, you know, however many hours it's been, maybe we think you might be here. So maybe now I make my circle there, as opposed to making my circle here. You with me on this? This is actually what we do in reality. So how do I come up with the specifics for my curve? Well, that's the technique we're going to be learning today. Now, it's interesting because most of you know Euler's identity, which is probably the most important identity literally in the history of history, okay? I've used this more than any calculus formula. Oops. Right, this describes the relationship between circles and triangles, between trig and exponentials, between hyperbolics, between inverse hyperbolics, between real and complex numbers. They're all related by one identity. And it's so cool and it's so important. But this one's really, really huge. This is called Euler's formula. Okay, so most of you have heard this. This is completely unrelated, but it's the same Euler. How many have seen the movie Hidden Figures? I have to think about the name. Unbelievable movie. Oh my God, that movie blew me away. I mean, like around 1960, these women were doing things without technology that we would have a hard time doing today with technology. I mean, they were doing calculations and computations. But during that movie... Yeah.
Isn't the movie about the space...
yeah, it's about these four women.
Yeah.
Is it 4 or 3? No,
it's 3. It's
three women.
One of them uses Euler's method.
But during the movie, there's two parts of the movie, and they refer to, at one point in the movie, they refer to, okay, I get all choked up. They refer to like eigenvalues and eigenvectors, and then later in the movie, they refer to using Euler's method. I was probably the only one in the movie who was crying, because this is what I teach. In fact, I think I taught both those techniques that week, and it's like, and my wife's looking at me like, what's wrong? They're talking about Euler's method. This is so beautiful. But it's, yeah. But back then, there was no technology to do things. This was very brute force, but it is a way of doing things. Now, Newton's method. I want to distinguish this from Newton's method. Newton's method, which is one of my absolute favorite techniques. And I teach this in Calc 1, and I use this. I have used this in multiple graduate classes. Newton's method, the idea is I have a curve, and it crosses the x-axis at an irrational coordinate. If it crosses at a rational coordinate, absolutely guaranteed you could find it, and it does not require calculus. It requires nothing more than, at most, pre-calculus. If you have a rational root, you can absolutely find it always, period, and it's never actually going to be that difficult. But what if your root is irrational? So then what we do with Newton's method, we say, well, then there's got to be consecutive integers that it crosses between. So what we do is we just say, let's take the halfway point, and then we find the value on the curve, and what we do is, let's say that's here, Then we draw the tangent line, and where the tangent line crosses, that's our first iteration, our first calculated value. Then we take that value, put it into the curve, and find where that tangent line crosses. And we keep doing this. Each tangent line is going to cross closer and closer and closer to the actual root. So I'm not going to go through the whole process. It's so cool. When am I done? Well, if you said I need a 3 decimal place answer, a 4 decimal place answer, a 5 decimal place answer, that's preset. What we do is each calculation we round to the preset number of decimals. And this is the only process you've ever done in your entire life where you intentionally round things and then use the rounded off value for the next value. So when am I done? When I get the same value on consecutive iterations to that many decimals, that means I'm going to get that value for eternity. And then that's my answer. And we used this actually for a really long time before calculators were around. The method's been around. I remember seeing this in high school as a way of calculating square roots. Very, very inefficient, by the way. Calculators are much easier. But it's an iterative technique where you use the same level of decimals on each individual calculation, and then when you have consecutive calculations, okay, that's really, really important. This is not that because we're not finding the specific value. We're doing iterations, and each one's going to be different, and each one's probably going to have more decimals than the one before. So we have to use our calculators a little more cleverly in this case. So the idea is, okay, how do I get the next calculation? Okay, now this line is called a trajectory. In Calc 2, I do what are called orthogonal trajectories. Did we do those in here? I can't remember. Did we talk about those? When we did separable differential equations? Okay, orthogonal trajectories is if I have a family of curves, it's all the curves that are orthogonal to those family of curves. So for example, if I have a bunch of concentric circles, then there's an infinite number of lines going through the center of the circle that'll all be orthogonal to the curves. Orthogonal trajectories means I have curves where the tangent lines are orthogonal. The curves themselves aren't going to be lines. A trajectory, most people think of a trajectory as a line. No, a trajectory is a path. It can be linear. It is certainly not required to be linear. So we are looking for trajectories in this case. Now the language isn't always clearly stated, but you have seen this before, okay? And a lot of you know I love bringing in movie references all the time. I mean, I can't prove the fundamental theorem of calculus without using the garbage pit scene from the original Star Wars. Remember where the wall's closing in on them? I actually use that to prove, that delta x, that wall is becoming one. I can't even talk about functions of multiple variables without using the cat in the hat. Duh, who are the sidekicks? Thing 1 and thing 2, which are clearly independent variables. Everybody knows it. So I go through all of this stuff. Well, second Star Wars movie, okay? The Millennium Falcon, remember they hiding on the big, wasn't the Death Star, whatever Darth Vader's ship was, they're hiding there. And remember they release the trash and they float away for a while, and then they go fly off, and then they get stuck in that asteroid field and they do all that stuff. So Darth Vader's in his little, iron lung thing, and the guy comes in and says, we've lost them. They've gone into the asteroid field, and you remember what he says? Asteroid fields do not concern me, Commander. Set a course on their last known trajectory. That is absolutely correct mathematics and engineering, and if you're going to be an evil star ruler kind of thing, you got to know this stuff. He didn't say set a linear path. That's not what he said. On their last known trajectory would be like what this was doing, and based on that, I am pretty sure, I think I saw in the background, I'm almost positive that the commander used Euler's method to figure out where to look for the Millennium Falcon. I could be wrong, but I'm thinking that would be the most logical guess. So the question is, how do we do that? That's the easy part.
A long time ago in a galaxy far, far away, though, so wouldn't that be before Euler's time?
It could have been an alternate universe kind of thing. I mean, you guys have all seen Doctor Strange, right? The whole, I just found out all of your dreams are just a different version of you in a different universe.
Oh, damn it.
That's crazy. And I think the dream version of me is having way more fun, I think, as a result. So we need to figure out where that next trajectory is. So the first thing we're going to do is figure out the equation of the tangent line. So I'm going to introduce some really, really wonky notation because we're going to be dealing with things that are not necessarily functions. I could be starting off with the circular path. The thing I'm talking about doesn't have to be a function, but I need to talk about the tangent lines. So the path we want to describe, this is strange notation. dy dx. Y is going to be a function of x, but we're going to write it in this form. In other words, with x's and y's, So think of it more like implicit differentiation. When you did implicit differentiation and you solved dy dx, you always had x's and y's on the other side, didn't you? And this is early Calc 1. This is not Calc 3. So early in Calc 1, implicit differentiation, you had x's and y's on the other side. So that's technically your f of xy. So I'm describing exactly the same thing. So that's my slope. Let's say this point right here, let's call it, well, how about x naught, y naught? That I know, that's given. So I need the equation of the line that passes through that point. So we're just going to use simply point slope formula. So it would be y minus y coordinate equals slope, which in this case would be f of x naught, y naught, times x minus x coordinate. You with me? So y then, and I'll write it y of x equals then this is the tangent line. Okay, that's easy enough. I now need my next value. Okay, so you notice I'm not even putting an xy plane here, but if this is an xy plane, we are going to move in very short increments. This would be preset. You would decide. So am I going to move maybe 0.1? Maybe I'm going to move 0.01. The smaller the increment you move, the more accurate your final answer will be. But if you're doing this by hand, it's also really long and tedious. Let's suppose what I need, if let's say x1 was the value 5, I need the value 6, or the value 5.5. Just I need some value that's not too far away. Am I going to count by 0.1s, by 0.01s? Doesn't matter, but I got to count by that amount until I get to my upper value. So if I'm going from 5 to 6 and I'm counting by 0.1, that's 10 calculations. But if I'm counting by 0.01, that's 100 calculations. We're going to count by bigger things, so we're getting the idea. How many here have ever written any kind of computer code, just at the lowest level, right? You do a do loop, what, on day 1, day 2 of your first computer class? This is a do loop. So in other words, the programming required to do what I'm describing is actually really, really low level. So if I'm doing this, man, I'm going by maybe 0.001 and doing it 1,000 times, but I'm letting the computer do the whole thing. I'm not doing any of them by hand. We're going to do them by hand, so we're only going to do a few at a time. Okay? So if this is the equation of the line, now the next value I use, I'm going to have a preset jump, whether it's 0.1, 0.01, whatever. That's my delta x. So x1 will be x0 plus delta x. In fact, in general, xi will be x0 plus I delta x's. I'm just going to count by the same amount until I get to my whatever my upper limit is. Most of the time, we're only going to move maybe a half of a unit or something.
Is I the upper limit? Or
No, I would be the first, second, third, fourth, fifth, sixth, whichever one I'm on.
just the end term?
Well, the last one would be my nth one, but I would need to know where I'm stopping.
Okay.
So what's x2? x2 is x0 plus 2 delta x's. x3 is x0. That's what I mean. So the ith one would be I delta x's. This is what we're going to do all the way through, and we're actually going to write each specific thing. But if that's the case, then what do? Well, now I go back to here. X minus x0 when I'm starting, that's 0, isn't it? But after one iteration, it's going to be delta x. After the second iteration, it's going to be 2 delta x's and 3 delta x's. So does everyone see this will always be I delta x's? Because I'm counting by delta x's. Does everybody see that? So this is going to be, this part's trivial. So the first time I do it, it's 0. The next time it's going to be whatever delta x is. The next time it's going to be 2 of those, then 3 of those, then 4 of those. Maybe 5 of them is my upper limit. Okay? But these are going to be newly calculated. Now, I'm using the trajectories to estimate the curve or the path that I think it's on. I'm not going to hit it exactly. That's not possible. I don't have all the information. I don't want to say it's your best guess, because it's not a guess. It's the most logical outcome. It's the highest probability outcome. It's the thing that's going to get you closest to the actual path. Is everybody cool with that statement? I know, it sounds kind of vague. So now, I want to calculate, okay, the next value I'm going to do is, we'll call it x1, y1. All right? Now, x1, y1 is a calculated point. x1's easy. That's x naught plus delta x. y1 is a calculation, And I am going to say, these are not equal. They can't be equal. It's my best estimation. It's not a calculation round off kind of thing. That's an approximation. This is an estimation, like asymptotic convergence kind of stuff. Is it possible they're equal? Yeah, but highly unlikely. When will they be equal? Well, if I'm moving on a line the whole time. That's about it. If I'm going on a curve, they're not going to be equal. But they're probably going to be really close. Now, what is y1? We'll go back to here. This is the tangent line through x naught, y naught. Oh, so when I want to do y1, I'm using those values to get to the next one. So make sure I write this correctly. So that's going to be, oops, sorry, the previous one. I don't need this anymore. Make sure I got this right. Now, then when I do x of y, or y of x2, which I'm going to call y2, that's going to use the previous y1. Now I'm going to use the calculated values. The first one's easy because the first line goes through the known point. Every other line is going to be, think of it as each line is going to be kind of bending as I'm going around. These are lines, but it's bending as I move, and the bend hopefully mimics the path that I knew it was originally on. That's the key. I have to know the original path.
That y of x1, is that the approximation, or is that?
No, this is the actual, let's call this the actual y curve. This is y of x. That's the path that it was on, and it got lost.
Okay.
I can't know that. I'm trying to estimate it. So what I'm doing is I'm using tangent lines. So I'm calling the points on the tangent line, the x1, y1, x2, y2, x3, y3. Those are points that I'm calculating. x naught, x1, x2, x3, those are easy because I'm starting with the known value and I'm adding 0.1 or 0.01 each time. That's a piece of cake. It's the y value is my estimation of the actual. This is the calculation of the y value, and it's hopefully really close to this.
Oh, okay, I get it. 'Cause
This
the
is
x
the
value
curve.
is always going to be exact. But
The x
y
values are not estimated exactly.
But the y values are what we're estimating.
And so as I continue, this will now be x1, y1, and I want to just show you as I go down the line, then let's call it the n plus first value, is that one. I'm sorry, is that which is the nth value plus the previous nth value. You're doing these one at a time, and this would be I delta x's. When do I, this was going to be, sorry, that's 2 delta x's. When do I stop? Well, I stop when I hit the last one I said I was going to do before I started the problem. We're going to do this in a moment. So now I'm going to bring this one up. This is the derivation. You already see this can be kind of tedious. The moment I start throwing numbers in there, it gets really ugly.
Those delta x's, like, those are always the same, right?
Yes, that's given before I start the problem. In real life, you would want as small a delta x as you could work with because the less change I do, the tighter I'm going to fit. But if imagine this technique has been around a long time. So go back to Hidden Figures, which was before, I think most of you were born. Most of you were born after 1961, 62, so it was somewhere in there.
A little bit after. A little bit.
Calculators hadn't even been invented. They were what were called adding machines. We didn't have technology that would do any of this. If you guys saw the movie, you'd realize literally the first computers came out, and the gigantic reels, and I think you could still count faster. But it's unbelievable. So they were having to do things. Well, obviously, first try. Really, they took like 30 in my other class. You can't do too small of iterations because each calculation would take you a long time. Plus, what if the functions you're dealing with are transcendental functions? What if you got sines and cosines and e's? How are you supposed to do? You see the basic problem people had generations ago? Now it's trivial. You have a calculator. My gosh, this thing is so fast with a calculator. All right. Well, actually, I want Mesa. Why didn't this go directly to Mesa? This is weird. Okay. Mesa College. This is where we should have started. Not now. So it's going to take a second. Here we go. This is why I wanted you to print this stuff so you could now hack it up.
Oh, I was really excited about Euler's method. I've been waiting to learn that ever since the first day of class.
Are you being sarcastic?
No.
Oh, okay.
I've been like, this weekend, I'm like, dang it, I wish we could have covered like Euler's week.
It's really beautiful mathematics when you have the technology in your hand. It would be nightmarish if you didn't have technology in your hand, because the calculations you can't do without, something.
It seems simpler than all the other methods.
It's less mathy. I'm a big fan of Newton's method because I know how it's used and how important it is, and how it's used actually in every mathematical subject, even though they won't tell you. It's how your calculators do things when they're doing, approximations. They just do it way faster than we can. So now, here's the problem that I want to do. Okay, I want to go. So here's my f of xy, x squared plus y squared. I'm telling you 0, 1 is on the curve, and I want to find the y value when x is 0.5. And we're going to do it with iterations of 0.1 at a time. So that means I'm going to do 5 things. This is kind of a typical problem. If you had the ability to write the code and it wasn't anything that you were challenged by, this would be trivial for you to program, but then you'd choose a delta x that was much smaller, and that means your answers would be different, and they would be better answers. We don't even know what the answer is. We can't know what the answer is. We can try to solve this problem, but this problem would be very difficult to solve right in front of us. It really would be. So it doesn't fit under any of the categories that we have, by the way. And the fact that it's nonlinear doesn't help us any. Okay, so here's how we're going to start. So I want you to notice, okay, see this right here? That statement right there? What's the 0.1 in front?
Delta x.
Yeah, sorry, let me go back to here. So I said in general, and I wrote it down over there, the n plus first iteration, right? That's our estimation for yn plus, yn plus 1. And what does that equal? That equals yn plus f of xn yn times the ith delta x. Okay. But in this case, all my delta x's, I said that bad. Really should be saying delta xi, not I delta. Okay. So because, where is it on here? Sorry. My delta x is 0.1. So every time I do the x minus the previous calculation, I said you're only counting by the same amount. So someone asks, is delta x always the same? This really should be sub I. My bad, I was writing I in front of it. But all of these are the same. Are there situations where the delta x changes? Yeah, Riemann sum. Oh, in Riemann sum, every delta x is different. But if you remember when you first started doing this, or let's say you were going to use trapezoid rule or Simpson's rule, now your delta x's were the same. They were all even increments. But delta x's themselves, in all situations, are not always the same. They're always the same in this scenario. Okay? So I'm doing that thing there. That's the 0.1 is my delta x. What I like to do sometimes is I sometimes will go ahead and distribute if it's convenient. It's not in this case.
So you're not multiplying delta x by the ith method?
No, I kept saying the ith delta x. That was my bad. I kept running I in front of it. It's because remember what was that? It was when we first did it was x minus x naught. Well, when I'm starting, that's 0. Now, if x1 minus x naught is my first one, and that's delta x. But then the next one is x2 minus x1, because now that's where the tangent line is going through. The next one's x3 minus x2. So every one of those is a delta x. So it was the first delta x, second delta x, third delta x. In this context, they're all the same.
Okay.
In general, mathematically, delta x's do not have to be the same as what I'm saying. In this case, they will be out of convenience. That's it. Just out of convenience, not out of accuracy.
So our notes from earlier behind the board there.
That should have been a subscript, yeah. Yeah, that was, I meant to do that, sorry. Yeah, I get excited, this excites me too, sorry to say that. So when we're doing this, the first calculation is trivial. But now I'm reusing the first calculation. As the decimal places grow, is there a problem with accuracy at some point, potentially? Yeah, in fact, can the decimal places go off the edge of your screen easily enough? They can pretty quickly because I'm squaring things here for one thing. So my favorite key on the calculator, of course, is the fraction key, and then maybe the parentheses key, but I have a new favorite that I use in this one. How many have used the answer key? That may be my favorite key on the calculator because that's the ultimate lazy key that most even high-level students don't realize. You'll do a large calculation, you will write it down, and then you will re-enter it into your calculator. You never re-enter a number in your calculator, ever. No, you use the answer key. It not only saves the number, but it saves a minimum of 3 decimal places past the end of the screen.
I use the memory key too.
Yeah, but then you have to save something, depending on how it's being used. So in this problem here, I did the first calculation, I got 1.1. So in round 2, I'm going to go ahead and enter the 1.1. That's easy enough. Nah, I just hit answer. Plus 0.1 times parentheses 0.1 squared plus answer squared equals. Now that's my new answer. So everywhere you have the equals in the next step, if you simply hit answer, you don't have to re-enter any of them. And why is this good? Because the decimals will grow, and they will grow very, very fast. It is not hard to be 20 decimal places at this point, depending on the nature of the function. But if I just keep hitting answer key, I haven't lost a single decimal. Now, I have to round off somewhere in the problem. And you guys all know this from math and science. You never, other than Newton's method, literally, that's the only technique where you intentionally use the rounded off value because you're trying to get convergence to that many places. Completely unrelated. Whenever you're doing calculations, you report a calculation, but you always use the exact value. If it's involving a square root of 2, you don't use an approximation of root 2, you use root 2. But when I report my answer, I will round that off. Only reports of the answer. So in this situation here, anybody know what that symbol means? The symbol's been around actually before you were born. We just didn't have the technology.
I thought that was a speck on my screen. I didn't actually realize it.
No, this symbol means approximation. This is exact. This is equals. Equals means it's exactly this. But that means this went more than 4 places. And I rounded it. Equals with a dot means you successfully rounded it to preset number of places, which in this case I said 4 places. That was arbitrary.
Oh, then what is the squiggly?
That means asymptotic. Think Taylor series, things like that. We just did a whole lecture today in my Calc 2 class where we were talking about limits, and then we talked about asymptotic convergence. Squiggled means things are asymptotic. So like a Taylor polynomial.
So
but
that-
in terms of calculation, there's a word that we use, estimate. So if I said, how far do you live from campus? Just give me a number. How far do you live?
Like 20 something miles.
Okay, good. So we're all going to go to your house after class. We're going to set our trip odometers to 0, and the moment they roll over to 20, we're in front of your house, right? No, you gave us a squiggle. You didn't give us an exact value. You didn't give us an approximation. You gave us a ballpark, a circa.
So then that symbol, the squiggly, is
This means this is an estimation of this. It cannot be equal, and regardless of how many decimals I go, it can't even be a decimal
so it
approximation.
estimates to, whereas the dot is.
I'm
is
gonna show you something that you probably learned as little kids and didn't realize it. Historically, okay, we know pi goes back to the ancient Greeks. They didn't have the ability to calculate it. They knew it was a little bigger than 3. We used the same estimator for over 2,000 years. Does anybody know what was used? And all the old textbooks have it. 22 sevenths. Why? It's pretty darn close. Yeah. 22 sevenths is an excellent estimator of pi. Okay? One day I was giving an exam in a class and I forgot to bring work, and I had like 2 hours and I had my TI-89 titanium to play with. So for 2 hours I played with finding better estimations of pi. I think that's the one I came up with. Try that on your calculator. No, I came up with this on my own about 10 years ago, and I've been showing that to people. Try that on your calculator. What do you get? Read it off to me, because
That's not it.
that's not it?
No.
Oh yeah, no, that ain't it.
Is it 113? I tried that. I can't remember what it was because I haven't used it in so long. Is it 113?
No, it's bigger.
Shoot.
No, it's a 5.
Okay, here's what I did. Multiply 113 by pi. I can't remember what it was because I haven't done it in so long. What happens when you multiply that? Do you get something really close to an integer?
356
Say again?
or 355. Yeah.
So it's this should be 355?
Yeah.
Is that the number?
Yeah.
All I know is that I came up with something, by the way, you can tell how often I use this. I was really bored, but I came up with something that I believe has 6 or 7
pretty
decimal
good.
place accuracy. But it's 3 digits.
No, 3.1.
You could keep going for the rest of your life and find rational numbers that are really close to an irrational number. That's why it'd be an estimation. That's why it'd be a squiggle. That's why Taylor polynomials, you could estimate the sine function with just x minus 1/6 x cubed. And we did that in class today. If I choose really small values for x, the decimal accuracy is unbelievable with the sine wave. If I go more terms, it's better. That's what that means. It means asymptotic, and it's only equal via a limit. But this, we're not taking a limit, so we're doing an estimation. It's ballpark. But here's the problem. So when I say how far, we'd say squiggle 20. Might be 21, might be 19.5, but we're just saying it's in that range of values. We're not giving any degree of accuracy to it. We're just saying it's close. That's what we're saying here. We're really close, but I can't say how close. So when we're doing the problem, you're using answer each time. So what I did was, I did not ever use the rounded off value. I used the value that filled up my screen. I report the rounded off value. But I understand the difference? But in this next step, don't use this value, use answer.
Yes.
Because otherwise you have guaranteed that the last decimal place will be different.
So the equal sign with the dot is the
That means
successful
calculator approximation.
Okay, okay.
That basically, because we have technology on our sides, we have not always had the ability to do that well. That's why when you were growing up, people didn't distinguish the estimation from the approximation because we didn't have technology either way. So we actually didn't know how accurate our answers were. So for all practical purposes, they were all estimations. If I gave you a decimal and had no ability to check it or calculate it, you wouldn't say, well, it's perfect. You'd say it's probably just close, right? And so there's the difference in the language. So at the end here, let's just suppose hypothetically that I had the ability to solve that original differential equation. We don't. But let's just suppose we did. Then what we'd actually want to do is go back, solve the differential equation, and figure out the y value if we use an x value of 0.5. Would it be that value? No. But we're hoping it would be relatively close, or the whole process isn't very worthwhile, is it? Now, if you had the ability, by the way, this is something you might want to try on your own, because this takes time. I don't want to do this in class. It's a waste of time. Go back and do the same problem, make that smaller, maybe 0.01. So instead of 5, it's now 50. It's a headache, it takes a while. And see what happens to this number. It's going to be very different. But whatever the actual answer is, it's closer. Now, you understand why I said the mathematics of something like a search and rescue. It can't be an exact science. Somebody's lost at sea. All we can do is say, this is our best estimation of where we believe they ended up. We start there, and then maybe we make a circle. Right? That's kind of the simple way.
Is there no way to apply like a limit as the variable approaches infinity?
Well,
into the
but
problem?
we are setting this ahead of time.
Okay.
We're not trying to solve the equation. We're simply trying to find a point on the curve.
Okay.
And what does that point mean? Let's keep this really simple. Let's call the x-coordinates time. An hour from now, another hour, another hour, another hour. Where are you in the ocean? Does that make sense? Oh, okay. So I don't really want a limiting process, but they've been gone for 5 hours now. They've been gone for 10 hours now.
Yeah.
What's our best estimation of where they are? And now we'll expand our search.
So each approximation is where they are at that hour, at that other hour.
If this is a good estimate, yeah, it's our best estimation of where they are. Is it exactly where they are? No. This is an exercise that I will not ask you to do. In Calc 1, it's really funny, when you first learn Simpson's rule and trapezoid rule, which are great ways of doing estimations of integrals that you can't integrate, because I can get ridiculous accuracy with just a few with a few trapezoids or a few Simpsons. Everybody knows what a Simpson is, right?
So
It's a parabola.
interval.
So anyway, I can get ridiculous accuracy. So if you go to the calculus books, what they mostly give you is problems you can already integrate. Why would you do an estimation if you can integrate and give the answer in a few seconds? Why would you spend a half an hour doing this estimation? What a waste of time. I mean, really, that is a waste of time. Only to check to say how good is this as an estimator. No, I can give you the exact value. Why would I estimate? So you only do problems that you can't find. So an exercise would be go to a differential equation you already know the answer to, that you've already solved, and try this. and see how good your answer is. Again, if you've solved the differential equation, then you're just simply plugging 0.5 in for x and saying, what's the y value I get? Are there initial conditions here? Yes,
Y is 0.
right there. Oh, okay, so I could apply this to something I already know how to solve. Again, in real life, would we do that? No, we already have the answer. Why would we estimate it? But it'd be a really good way for you to see the power of the technique. See what I'm getting at? And that's what I would, this is where I would do, now let's do 0.01. Let's do more iterations and see how close we are to the answer that we now actually do know what it is. And every time I make delta x smaller, my estimation becomes more powerful, more accurate. That would be simply an exercise to convince you of the power of this. I did a very softened example because 0.1, doing 5 calculations, you know, I'm sorry, but you're probably still lost at C then. No, we'd need to get that tighter, but at that point we need a computer program. Right? We're not doing this by hand, and we're having the computer do this. I mean, why not make delta x microscopic and have the computer do a bazillion calculations? It's no sweat for us, right? For I equal 1 to 10,000 do. You get your do loop and you're done in a few seconds. I mean, that's more real life. Now we go back to hidden figures. They were doing this problem without computers, without calculators. They were doing this pencil and paper. Or I should say, she was doing this pencil and paper. That's just mind-numbing to me, that, you know, the brain power that required. I mean, if you think about it, you're like, so go back and rewatch that after doing this, going, oh my God. And the equations they were using were a little more complicated than this one. I chose something that would be relatively easy for you to follow. So now that you can do this on your own, it's just an algorithm. But it's a powerful algorithm because it can be applied to really big problems. But I would strongly urge you, if you're doing that, you know, use a computer to do the calculations. And then everything else is much, much easier. Okay? Now, the other thing we're going to do today, okay, we're going to do something called the Wronskian as opposed to the Wrightskian. No, that's not it. I know, that's bad.
We need to get more.
First of all, what is a Wronskian? What physical tool are you actually using when you do this? Do you remember?
A calculator.
Something from linear algebra. It's a determinant. It is a determinant, but it's a determinant of something very specific. So I'm going to go through really quickly and derive the rules. You do not have to repeat this. But I do not like people just accepting important theory at face value if I can demonstrate exactly what's going on. So the Wronskian, by definition, is a determinant, and it's a determinant to make a conclusion about something. So here's what we have, okay? Let's see. I'll say, I'm sorry, A-N, so not A1, A-N minus 1. Now, 0 is important. So it's an nth order, linear, homogeneous differential equation. It does not have to have constant coefficients, but at this level, if it doesn't have constant coefficients, it would be way out of our price range. Right? It would be way above our pay grades. It's not that it's impossible, we're just not going to learn how to solve that one. We'll be able to solve second order when it's not constant coefficients, but after that, it's just too messy. So I've solved this differential equation. So the first thing is, we're going to say that y1, y2, yn, I got these solutions. I can't show you this today. This is actually 2 lectures from now. I can prove to you exactly how many solutions we could get. Well, actually, I guess technically I could come up with 1,000 solutions. Like, what if one of your solutions was the sine function? Maybe 2 times the sine function will also work. And one of your solutions is the cosine. And another solution is sine plus cosine. And another is 3 sine minus 5 cosine. All of these will work. If I start doing, those are called linear combinations. If I start doing linear combinations, I could do this forever. So I don't want linear combinations. What I want are
Linearly independent.
linearly independent solutions. And that's a very important word. That's one of the few words that we have to know from linear that we use in this class. Linearly independent, quite literally in simple terms, if I only have two things, if they're not multiples, they're linearly independent. If I got three things and none of them are combinations of the other two, and so on and so on. So I have three solutions. One of them's sine, one of them's e to the x, one of them's cosine. Pretty sure I can't get one from the others. But if I had three polynomial solutions, maybe one of them's a combination of the others. But I can't tell by just looking at it. So what the Wronskian is a determinant that allows you to determine if the solutions you have are linearly independent. And the Wronskian looks like this. We generally write it W of x. Wronskian, I'm using x as my variable. The first line are all my functions. The second line are all my first derivatives. Now, second, third, fourth, fifth, how many derivatives do I take? This is not a trick question. Anybody want to try this one?
N minus 1.
Why n minus 1?
Square.
Because it's got to be squared. You're right. Because think of the first row as the zeroth derivative. Does that make sense to everyone? Why I got to do n minus 1? So this is n minus 1 y1 dx n minus 1 all the way over to dn minus 1 y n dx n minus 1. This way I have n columns, I have n rows. Now, I do this in linear. I've never done more than 3, and in this class you're mostly going to do 2. So that's not the difficult part. This is the part I'm going to prove in a moment. The value of the Wronskian. Now, how many did Wronskian in your linear algebra class, by the way? You have two choices for the value. What is it?
0.
0 or
1. Infinity.
not 0. It's 0 or it is not 0. That's it. The value of the Wronskian is either the number 0 or it is not the number 0. It doesn't matter if it's a function that might be 0. No, it's identically equal to 0 or it is not. Now, something you might remember from linear algebra. If any row or column of the determinant is a multiple or combination of any other rows or columns, your value of your determinant will always be 0 because you can do combinations to get a row or column of zeros. And determinants, you can do column operations, not just rows. Okay, so the definition of linear independence. I'm never going to ask you to prove this in an abstract setting. Those n solutions, and these are, by the way, the y's are functions. They are solutions to my differential equation. They are trig functions or exponentials or logs or polynomials. They're things that we're used to using. There's nothing crazy. Okay, c1y1 plus c2y2 plus all the way to cnyn equals the number 0. Absolutely, this has a solution. The c's are constants. Tell me a solution for this without even thinking.
0.
All the c's are 0. We say this set is linearly independent if and only if the only solution to this is all the c's are 0. That's the definition. Well, I've had a lot of people tell me they learned a different definition. No, those might be things that are true if this is true. No, this is the only definition of linear independence there is. If I set up a linear combination equal to 0 and the only solution is the trivial solution, that's where the term comes from, all the c's are 0, then they're independent. Now, let's suppose without loss of generality that y1 is a combination of the other guys. That would mean it's dependent. By the way, it could have been y2, it could have been y10. Well, whichever one it is, rearrange it and make it the first one, okay? So that's really not a thing. So let's suppose that y1 is a combination of the other guys. That means I could rewrite y1 as negative c2 over c1y2, negative c3 over c1y3, down to cn over c1 yn. Does everyone see that? I threw everything on the other side and then divided by the c1.
Okay.
You with me on that? So go back to this statement here. What is now going to change in this statement? This column is now going to change, isn't it? Because instead of y1, I'm going to write this. And isn't the derivative of a sum the sum of the derivatives? So won't this now be the same linear combination, the same constants on all those derivatives? And then the next one will be the same combination on the second derivatives, and on and on and on and on, which without me actually doing, I physically do this in linear, I'll rewrite the whole first column using that, and then it's very obvious that the first column is clearly a linear combination of all the other columns, meaning the value of this determinant therefore is 0. So if the value of the determinant is 0, then they are dependent. If the value of the determinant is non-zero, then they are linearly independent, and that's what a Wronskian is used for. It is used to determine if a set of solutions is linearly independent, yes or no. So far, so good. That's what you were supposed to get in linear algebra. We don't spend a lot of time because we don't really have a lot of examples. When I do this in linear algebra, I do second-degree polynomials because the derivatives are real easy. It's really easy to... But in this class, most of the time it's sines, cosines, exponentials, things of that nature. Not a big deal. So here's where we get into a little bit of trouble. And even in linear algebra. So you just did your Wronskian. You did everything well. And you came out and the value of your Wronskian, let's say, was this. You did the whole problem. You had a huge problem and you did the determinants of all your derivatives and you got this. Is this equal to 0? Did I write the number 0 on the right side? No, so this is not identically 0. Where everybody gets confused, but there are values of x that are 0. Are there values of x that it's not 0?
Yes.
Then it's not 0. But can it be 0 somewhere? In linear algebra, you would stop right now and say, this is not 0, therefore my set is linearly independent. Period. You're done. You walk away. Because we don't have any other use for it. In linear algebra, we're only interested in how to prove things are linearly independent. We're not solving the differential equations in linear algebra. I just said, here's a set of solutions of a differential equation. That you don't even care what the differential equation was. You just have this set of functions. No, in this class, we're actually going to solve. We're going to get these. So let's go back to this. Is it possible that this is 0 at some point? When is it 0?
1 and -1.
Whoops, sorry. I want it to not be 0. Yeah, so x cannot be -1 or 1. That means we've just partitioned the number line into 3 intervals. So my Wronskian is not 0 in each of these 3 intervals. You with me on this so far? That means my set of solutions. Remember on the very first day of class, like I said, your interval of solutions? The interval of solution where this differential equation is valid is one of these 3. It can't be more than one of these 3. How would I know which one to choose?
Based on your initial.
I'd have to have an initial condition. And I told you in my initial condition, y of 4 equals 10. Well, the fact that I used positive 4 means it must be the last one. What if I said y of 0 equals 6? Then it's got to be the middle one, and so on. This is where this class differs from linear, because in our class, we do care a little bit where this equals 0, because what it does is it limits the solutions. What if my Wronskian were, and my Wronskian is e to the x? Is there any value that e to the x is ever 0? Nope, that means my interval of solution is
All real numbers.
all real numbers. We love that one. What if my Wronskian is log x? Well, then my interval solution would be only positive numbers. And so on, and so on, and so on. So if the Wronskian can be 0 at certain values, all that does is it partitions the number line. You don't choose which one. That's really chosen for you, and you would need an initial condition. Okay? So in linear algebra, all we care about is either the number 0 or it's not. In our class, if it's not equal to the number 0, but there are values that make it 0, we throw out, because that is a restriction. I no longer have the set of real numbers as my answer. I now have intervals. That's not a big deal. And in our class, because the majority of the problems we're looking at are going to be second order polynomials, our Wronskians are going to be basically, most of the time, 2 by 2s. That's kind of simple. Now, the thing is, nowadays you can't be sitting here unless you had linear algebra, so your ability to calculate a simple determinant is not something I'm worried about. That's not a major part of this course. It's one, in fact, I could care less if you'd ever seen a Wronskian before. Now I just showed you what it is, and now you know what it is. But your understanding of something like linear independence, that is huge. Right? That's a major thing that you understand linear independence, because that defines things. if I gave you solutions that were dependent, they were multiples of each other, or I gave you three and one was a combination of the other two, that means I haven't completely solved the problem. Well, is that important? When we get to the eigenvalue, eigenvector portion of this course from linear algebra, it'll determine whether I can actually answer the question or not. If I don't have enough linearly independent solutions, there may not be an answer to the question. There's certain things we want to do, and it's possible I don't have enough in certain situations. Question? Started to ask one.
Oh.
Yeah.
Okay, so just to make sure I understand, the linear independence is where we have a set of solutions that are not going to be equal to one another, no matter how much you try to chop it up, or is it
Equal to it? No.
or like that are similar or
No,
the same?
no function is a linear combination of the other functions. Linear combination has nothing to do with being equal. No. One function cannot be written as a combination of all the other ones. You're never going to say sine x and then I have sine x and then hey, it's the same one. No. It's I have a function, and this function's a combination of the first two. Let me give you a really simple example, okay? I've got 3 second-degree polynomials. Let's say I have 3x squared minus 4x plus 5. I have negative x squared plus 2x minus 1, and I have x squared plus 3. Okay? I gave you 3 second-degree polynomials. I would like to know if these 3 polynomials are linearly independent. By the way, the fact that I gave you 3 means they might be. If I had given you more than 3, they wouldn't. This is a linear algebra. They come from the vector space P2, which we know has dimension 3. If I gave you too many, it wouldn't be. Can I give you too few? Sure. If I only gave you 2 and they're not multiples, that's easy. Everybody got that? If I only give you 2 things and they're not multiples, independence is an easy thing. I don't have to do any work. But once I get 3, none of these are multiples. What if I gave you 5 things and the 5th thing was 2 of the first and 3 of the second and minus 4 of the third and plus 7 of the fourth? Do you think you could just look at it and see that? Probably not. So let's do the Wronskian. I'm going to walk you through because it's not complicated. So I start by putting these guys up top. This is exactly the kind of problem I would do in a linear algebra class. All right. Next row are their derivatives.
X minus 1 negative 2x plus 2x.
And the last row would be the next derivative. The nice thing about determinants, and this goes to the fact that if you have a matrix and you have its transpose, they have the same determinant. You can only do row operations on a matrix, but you can do row or column operations on a determinant because a column operation on the determinant is a row operation on the transpose, which produces the same value. I proved that in 254. So column operations might be easier than row operations here. So why don't I do something like this? Let me use that, and let's go sideways. And I know this is not new for anybody in here, this part. So let's do, let me do negative 3 of this column added to this column. And how about this column plus this column? Because I'm looking for zeros. You always want zeros. The moment I have a row with zeros, then I can expand really easily. Could I expand right now? Yes. Should I?
No.
No, when I ask this question in linear, 2/3 of the people will do column operations and make it really easy. The other third will expand this, fill up 2 pages, and none of them will get it right because they made so many algebra errors because they're multiplying trinomials. And I'm like, what are you doing? Yeah, it's legal. It's foolish, but it's legal. No, let's do column operations. So if I take negative 3 of these and add them, well, the bottom row would be 0. Let me put the 2x. This is what I would do. All right. Take negative 3 of these and add it, and what would I get?
Zero.
Just negative 4. Negative 3 of these would be negative 3x squared minus 9.
Zero.
So that would be negative 4x minus 4. Does that look right?
Yeah.
Now let's take this column and let's add it to this column. And that would be 2x plus 2. The value of this is equal to the value of this because those column operations will not change the determinant. The only way I can change the value would be to swap or to multiply by a scalar. I did neither. Now, can I go ahead and just evaluate this?
Oh my gosh.
Yeah, I got two zeros.
Yeah.
I can keep going, but I can evaluate it. So, plus, minus, plus, minus, plus. So this is 2 times. I'll be lazy. I can keep going. I can keep doing things, but I guess we'll just evaluate this. What are we going to get? So negative 8x minus 8 minus this, so plus 8x plus 8, and oh my goosh. How in the world did we do that? Okay, what is your conclusion in words?
All
Those
these
are
are
multiple.
linearly-
This set is
linearly independent. Oh, linearly dependent.
linearly dependent. This set is linearly dependent because I got a Wronskian of 0. How in the world did I do that? Well, if you take this and you add it to 2 of these, you'll get this. That's about how, that's my speed right there. I made sure that the third one's a combination of the first 2. But is the third one a multiple of them? No. That's why it's hard to just look at it and see.
Instead of like doing all that and making it equal 0, could you not just do the like, like you multiply the columns and then you multiply the columns and add them and then you subtract the columns going down?
I've never done that or shown that in my life because that's about, no exaggeration, about 6 times as many steps algebraically as just simply evaluate. First of all, just evaluate it straight up. If I gave you a 3x3 with numbers, I show people how to do the entire problem from beginning to end in certainly less than 20 seconds. What you're describing is more like 5 minutes, and almost 100% of the time people get the wrong answers because they created 6 products and had to subtract 3 sets of them, and nobody ever gets it. It's the worst way imaginable, plus it only works on a 3x3. It doesn't work on anything else. I'm not joking. I've never done that. I've never taught it. I've fortunately never had a class that did it. And I'd rather you be done really fast and be correct. We'd still be working on that one, by the way. You really want to set up 3 columns and multiply 3 sets of trinomials 6 times. And I'm not joking. That's what you're describing. 6 sets of multiplications between 3 trinomials at a time, and then correctly distributing the -3 at a times. I'm saying, laughingly, it's like, who in the right mind would choose that? You are adding, it's about 6 times as many steps algebraically, and no one ever gets it right, even when it's just numbers.
Sorry, are you talking about cofactor expansion?
No, there's a trick. It's an evil scheme that people say, well, if I rewrite this and I do all of these algebras, I'll get the right answer. Yeah, but you've added about 1 million steps to a problem unnecessarily. Doing row or column operations on a big one is always the fastest way if you can. Could I have done another?
Yeah. We get
Could I taken 2 of these and added it to here and got zeros?
Yes.
Then I have zeros.
zeros.
That would have been easier.
Or could you even just go, this column is twice as big as this column. My answer is going to be 0. Could you say that?
Yes.
Yeah. I just went ahead and did it. I'm a big fan of doing column operations because otherwise I'm dealing with larger things early. Now, I did polynomials. What if you've got trig functions and exponentials, which is probably the more likely answer, maybe occasionally a logarithm. You say, well, won't it be totally obvious? Yeah, but what if one of my answers involves, let's say e to the x times sine x? And then another one might be e to the x times cos x, and another one might be something else. You say, well, won't that be easy? Yeah, but now when I do my derivatives and I have product rules and chain rules, you can start seeing how this can be really convoluted really fast. And it might not be entirely obvious. So the Wronskian is a really, really simple check. In our class, for the most part, our Wronskians are going to be 2x2 because the majority of problems we solve are going to be second order problems, which means you're only going to have 2 solutions. So the Wronskian, the actual doing it will be trivial. So why would we do it? Because the actual value of the Wronskian determinant shows up in many of our answers. We're going to do a problem, we're going to solve it, and you're going to go, oh, that denominator is just the Wronskian. That's going to be a common thing. Oh, the Wronskian is not just a test for independence, it actually shows up in the answer. And of course, it's not 0. Right? It can't be 0. And so the Wronskian is going to be one of the more common things we do, but only for 2x2s. So it'll actually be simple most of the time.
Sorry, so the number of answers that we have in the differential equation are the degree of the.
Yes, the degree of the differential equation determines the number of linearly independent solutions. That's, now, determining the specifics, right? We have arbitrary constants. That is a function of the initial conditions. That's the least important part of the problem. So starting, I think where we are right now, Monday, I'm going to prove that to you. Now remember what I said the conditions were. Right now, it's got to be homogeneous. It has to have constant coefficients. We will add to that. We solve the homogeneous first with constant coefficients, then we go after the non-homogeneous with constant coefficients. Then we go after the homogeneous with potentially like, x's to powers as coefficients, but only x's to powers. And then we go after the non-homogeneous with x's to power. We work our way up so that when you look at a problem, you'll know exactly what to do, but determining the number of solutions, that's trivial. So where it gets kind of tricky sometimes is when you're looking at a problem, you're going, but I'm only seeing 2 solutions, but I'm supposed to have 4 or 5. Well, there's ways of doing this. What's that?
Eigenvalue?
Not exactly. That's a different animal. It's sort of from the same universe, but not exactly the same. It's actually something as simple as solving polynomial equations. Not differential equations, polynomial equations. Solving homogeneous polynomial equations and figuring out the roots of the polynomial equation is going to be kind of the algebra we do to figure out our linearly independent solutions. When we get there, which is next week, you're going to love it. It's going to be so cool. You're going to say, that's so easy. We have to prove it. We have to derive it. And once we do, you'll say, wow, it's right there in front of me. But I've thrown some major conditions at you. I said it has to be homogeneous, and right now only constant coefficients. Well, but that's not the universe we live in, right? I mean, you guys saw first order linear. Those weren't constant coefficients, right? But that was also a first order differential equation. If that had been second order, that would be a lot trickier. So we're going to learn a technique next day that's going to take those second order ones that we couldn't solve today and make it first order. It's got a really clever name. It's called reduction of order. It's where I take a second order through the appropriate substitution. I make it first order linear, solve it, and then go backwards. But it's a very, very specific one. It's the first of the new techniques we're going to learn. And then everything else will fall in. And they all look different enough that it's not hard to classify them. And unlike what you just got done doing, I don't think there's many crossovers. I don't know if there are any crossover problems. Right now, you already know. You might have a separable that also looked first order linear, that also may have been exact. Heck, it might have even been homogeneous over a particular degree. There were many problems that fell into multiple categories. You actually like that, by the way. That's not a bad thing. Because in whatever one you see first, whatever method you see first, or whatever method you feel the most confident in. But often it's the case where you don't have choices, most of the time. This is what it is, this is what I got to go with. And that's why I said there was the hierarchy. Right? What do you always look for first?
Separable.
Separable, because if it's separable, you're probably done in 30 seconds. I mean, literally, there's not much to do. It's separable, I'm done. And you kind of go that way. No, it's not that, it's not that, it's not that. Okay, well, it is homogeneous of degree 7. Well, that's not going to be fun. Well, So we're going to do that. We will talk about the exam in a week, though. The exam's still a ways off. I don't like talking about the review too much, but I'm already getting a lot of questions about the exam. I believe the exam and the practice test are up. Now would be a good time to start checking it out. What we did today looks so different from everything else that if you can do the other stuff, you're probably in good shape. We're just adding one thing. And the stuff we're adding today is of a much lower level in terms of complexity. We will do new stuff on Wednesday. We will do new stuff on Monday. We will also review on Monday. That's where we go over anything you have from the practice test, unanswered questions. The only thing I care about in terms of prep is that you come to Monday's class having taken the practice test. If you don't, oh boy, that's so dangerous. People do this. I'll do it the night before. And what happens when you get stuck? When you going to fix it? No. Monday is kind of your last true opportunity to ask meaningful questions. So, on Wednesday, an hour before the test, Benito's going to text me a differential equations question. Because that's what it feels like sometimes when you can't type a differential equations question. I got to see the problem. So when we're in class, I want specific questions, not vague, ambiguous things, because there can't be any mystery.
What methods are we expected to know? Like how many?
Well, right now, what do we have, 5?
Yeah.
And really, there's three that just stick out. You don't have to do anything, right? If it's separable, it's separable. If it's first order linear, if it's exact and you checked it, it's exact, those three are automatic. When does it get trickier?
Bernoulli.
It's
not exact, then it's.
It's not exact, but I can find an integrating factor. It's Bernoulli, so I have to do a substitution to change it. It's homogeneous of a particular degree, I have to do a substitution to change it. Those ones each require an additional step. There's still technically 5 techniques, or I guess Bernoulli would, because exact, where I have to do an integrating factor, is still considered under the umbrella of exact. We don't like that one because when I'm testing for exact and it's not exact, a lot of times I think, okay, you didn't do anything right. But a lot of times you'll have one of your terms might be really simple and you go, oh, you know, if this shows up in a quotient, I think everything's going to cancel, you know, and you go after it. But that same problem might still fall into one of the other ones too. I think for most of us, that's probably the one, and I know for me, that's probably the one that's the most troublesome because it's the only one that I can't see on the first step. Bernoulli I can see on the first step. I just see that extra y term. Homogeneous, everything's the same degree. It might be something else, but if I see it's homogeneous, I might go after that because one step later it's first order linear. And that's one that hopefully you all feel very comfortable with. So that's the things over and over and over again, you know, that sort of stuff. And it's all about categorizing the problem, as you know. Once you see it, which one is it? Now I know my plan of attack.
Can we have a note card with it?
Yeah, we'll talk about that when we review. I'll tell you what you can bring and stuff. You don't have to do anything, but there's certain things you've learned in this class that you may not know inside and out. Of course, you all know the formula for finding the integrating factor to make something exact, right? You all know off the top of your head, right? It's my and an nx, and it's divided by something. Yeah, you know that, right? And there's a negative maybe somewhere, and there's an integral probably. Yeah, that's probably one we'd want to write down, right? Because that's not hard to do. It might be hard to remember. Okay, let's go ahead and